Okay, so 10.5 is the counting problems involving not and or. And so this is where we're going to consider the complement and union of different sets. And hopefully those two words you remember, or at least you have a tingling in the back of your mind when you hear the words complement and union, because those are straight out of chapter 2 of this class. And we even talk about unions and intersections back in Math 20 in 10.1 in that class. I actually just taught that lesson in my Math 20 classes yesterday. So if you want some refresher on intersection and union, you can watch the Math 20 video from 10.1, or we also have all the videos from chapter 2 where we did nothing but sets. And so the complement is our not. This little table up here I thought was neat because it connected set theory with logic with arithmetic. When we do complements or nots in math with arithmetic, with our numbers, we're actually doing subtraction. When we do unions, remember unions is where you take one set and you take another set and you combine them all together. That's an or situation because you have to live in either one set or the other set, or you could live in both in order to live in the union. So that arithmetically looks like addition. So there's a neat connection where all of these concepts actually do overlap and intertwine. And I liked that it involved that because sometimes it's easier to think about it in terms of complements and unions. Sometimes it's easier to think about it more in a logical sense. And so you're going to be able to do that today. The problems involving not, that word not, are going to be complement problems. Now, your problems aren't necessarily always going to say not. What it's going to be is that the easiest way to come up with the solution is by thinking of the complement. If we are doing a card problem and I want to know what is the, how many different ways can I pull out a red card, I can either think about pulling out a red card or I could think about not pulling out a red card. And depending on how the problem is set up, one way may be easier than the other. There are times that we will use the not instance, and there are times when logically it makes sense to just think of it more straightforward. But really these nots and ors allow us to approach a problem from a different perspective. And a lot of times those different perspectives save us work in the long run. It makes it to where we don't have to list out, 150 different sets, or it just makes it easier for us to approach. So the number of ways in a certain condition can be satisfied by the total number of possible results minus the number of ways the condition would not be satisfied. So I think that it's easiest to remember back to chapter 2. In chapter 2, when we're dealing with set A lives within the universal set. And so if our elements are involved here, then they live in set A. But we can think of the not portion as being anything that lives in the universe that's not in set A, and we call that the complement. That was the A with the little dash or prime indicator here. So we can actually figure out what lives within this set. Even if we don't know, we can figure it out if we know what lives in the universe and what doesn't live in that set. And so that's a way to approach it. You are going to have to find subsets and proper subsets again. Again, I really like that chapter 10 falls towards the end of the semester and it ties in all the stuff from chapter 2 because that should be refreshing you on this material. The number of subsets were found by 2 to the n power, where n was the number of elements within a set. And then the number of proper subsets was 2 to the n and then minus 1. Because to be a proper subset, we couldn't include the entire set as a subset. That's why we subtracted 1 from it. The entire set A can be a subset of itself, but the entire set A cannot be a proper subset of itself. So that's where the minus 1 comes in. Again, all of that stuff's from chapter 2. But we're going to approach our problems today from this not perspective. This first problem, though, straight out of chapter 2. Find the number of proper subsets of our set S, which includes the elements A, B, C, D, E, and F. When we find proper subsets or just the number of subsets, all we really need to know is how many elements live within this set. We have 1, 2, 3, 4, 5, 6. So our n in this case is 6. And since it wants proper subsets, I'm going to take 2 to the n minus 1 to find the number of proper subsets. 2 to the 6th power minus 1, 64 minus 1, which is 63 proper subsets. Some of your problems are just like that. Just finding the number of subsets, or proper subsets. And we're going to use this kind of backwards thinking or roundabout thinking to help us figure out these other problems without having to list out all of the possibilities. It says if 4 fair coins are tossed, in how many ways can at least one tail be obtained? This is using the fundamental counting principle that we learned 2 sections ago in 10.2. The fundamental counting principle is where we say, okay, how many options do we have for each of our tosses? We're tossing 4 different coins, and each coin we're going to say only has 2 options. It has hails. I guess that would be a combination of the 2. Heads or tails. Those are the 2 options. That's true for the first coin, that's true for the second coin, third coin, and fourth coin. And so the fundamental counting principle said that we could take 2 to the 4th power, because there was only 2 options. There's 4 coins, and we can figure out that the total number of possible ways for these to turn out is 8. That doesn't seem right. 2 times 2 is 4 times 2, that's 16. I don't know why I wrote 8. 16 ways. Probably because I did it in my head. But that's how many total options there are for tossing 4 coins. That does not tell me how many ways can we get at least one tail. And if I wanted to figure out how many ways we could get at least one tail, one way, the exhaustive way, is to write out all of them. Do our trees or make a list where we have, okay, we toss all the coins and they all land on tails. We toss all the coins and 3 land on tails, and so on and so on. But that's exhausting. And so our new method of thinking about the not will actually shorten this process for us. If it says we need to find how many ways at least one tail must be obtained, then the only not, or the opposite, the complement of at least one tail, means all heads. If they're all heads, there's no tails. All heads is the only way that no tails ever pops up. Every other option will have 1, 2, 3, or 4 tails. Well, if we have all heads, there's only one way to get that, right? All 4 coins have to land on heads. There's no other way to not get at least one tail. So I'm going to subtract the complement of at least one tail, which is one way of getting heads, 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 and heads. This all heads option is the complement of getting at least one tail, which gives us 15 ways that we can come up with this. There's 15 options of getting at least one tail. Paying attention to the words at least, at most, more than, less than, those are the big important words in this section. And they're going to tell you which way to head to find the complement. Because oftentimes the complement is a lot easier to find. I had to list out one way of all heads instead of finding the 15 ways that actually did work. So it cut our work quite a bit. Any questions on any of this so far? On complements, on the sets? We're going to see how this all really connects in just a second, especially when we use or. All right, let's do a plain problem. There's a problem like this on your homework. It says Carol and her 3 friends are boarding an airliner. There are only 10 seats left. 3 of them are aisle seats. How many ways can the 4 friends arrange themselves in the available seats so that at least one of them sits in the aisle? Okay, so we've got quite a bit going on. And I really don't want to have to list out, especially when you see the solution, you're not going to want to list out all the different possibilities. But there's a couple of words in here that are really important to pay attention to. One of them is this word arrange. That's from 10.3. 10.3, we ended with a nice little table that showed the differences between permutations and combinations. They were really, really similar, but permutations dealt with the order of things. The order mattered, and we couldn't have duplicates. You know, Carol can't occupy 2 seats on this airliner. She only gets 1. She bought 1 ticket. So the word arrange tells us we're going to be doing permutations. You can still do permutations and combinations in the fundamental counting principle here with our ors and nots. The ors and nots are just having us focus on kind of what's not included in the problem instead of what is. So we're going to be doing a permutation. And here's how this problem is going to work. The first thing we need to know is we need to know how many different total arrangements can we have. On the last one, we did that. We found the total number of possibilities for our head coin toss. We needed the total. And then we're going to subtract when the requirements aren't met. That's our not. And that tells us our solution. This is really just rewriting in words. Which part can you see? Right here. The A equals the universe minus the not. We need the total minus the not minus what makes stuff doesn't work, and that gives us our solution. That's what we're going to do here. That's what we did on the last problem. We need to find the total number of arrangements of the friends. Then we're going to subtract what happens when all the friends are not sitting, if at least one of them is not in an aisle seat. And that will give us the total possible arrangements of at least one friend sitting in the seat, in the aisle. So the first thing to do is to find the total number of arrangements. And that word arrange tells us permutations. There are 10 seats total, and we're going to select 3 of them, or arrange 3 of them at a time. No, 4 at a time, excuse me, because Carol and 3 friends. That's 4 people. So we have 10 seats. That's our N. And then Carol and her 3 friends equals 4, which is our R. NP.
Is N always usually bigger than R?
It has to be. Yep, it has to be. Your total number of selections has to be greater. If I have, which this is more about combinations, but if I have a bag of 4 balls, I can't reach in and pull out 5. So yeah, it's always got to be bigger. So if my N is 10 and my R is 4, to find the total, I'm going to have to do 10P4. That'll tell me the total number of possible ways to arrange these 4 friends in these 10 seats. If you type that into your calculator, you find that that is 5040. There's 5,040 different ways that Carol and her friends can take these seats, because order matters. The arrangement of the seats matters. But now we need to consider what happens if they don't get an aisle seat, because we want to know if at least one of them is going to get an aisle seat. Well, there's 3 aisle seats available. So if I pretend that Carol and her friends don't sit in those 3 seats, that's like removing 3 seats from our total. Then there's only 7 seats for her friends to sit in. Does that make sense? We started with 10, but we're going to pretend they don't sit in any aisle seats, because that's the opposite of what we're looking for. So what I have to end up finding then is I have to find 7P4, where I consider only the non-aisle seats. Because if I consider the non-aisle seats, then that's going to help me figure out how many possible arrangements will include at least one aisle seat, without me having to list them. If you do 7P4, you'll get 840. So to find the solution, or how many different ways is there for them to arrange themselves so they get at least one of those aisle seats, you subtract the 2 and you find that there's 4,200 different ways. Aren't you glad we did not have to sit there and play with a map and arrange them? So we found the total, and we're subtracting all of the instances where it doesn't work to find our actual solution. You have an airplane problem. What's another problem? I'm looking. There's also an album problem and a restaurant problem that work similarly on your homework. Basically 13 through 16 on your homework is problems like this. Are there any questions about what we did? Because those were the ones with the knots. Those were the ones where we actually considered the opposite of what we wanted to find out to direct us. And it saved us a ton of work. All right, let's look at OR. OR is going to involve unions, combining sets. I like OR. I think OR is fun. I think OR is very logical. But we have to be a little bit careful with OR. Because when we combine two different sets, we have to be aware that those two sets could have some things in common. And if we don't consider that, then what ends up happening when we're counting is we'll double count. So I'm going to look at the pictures first, and then I'm going to look at the equations, because I think the pictures help the equations. When we do unions, there's two different kinds of sets we can have. We can have non-disjoint sets, that's sets that overcross somewhere, and we can have disjointed sets, sets that don't cross at all. If we are unioning these two sets, they don't have anything in common, so there's no risk of double counting. These are good. We don't have to worry about it. Over here, they have that shared middle section. So if I'm trying to figure out the total number of students enrolled in English and math classes, I have to be careful not to include the students who are enrolled in both at the same time. If I counted them with the math students, I don't have to count them again with the English students. And so that's why we have two different union formulas. We have one for non-disjoint sets, where we have to subtract out their intersection, and we have one with disjoint sets. Disjoint sets, you just add them up. It's easy peasy. It's the non-disjoint sets that we have to really watch for this intersection and make sure that we subtract that off so that we don't double count. Does that make sense, the double counting? We're going to use these formulas moving forward to help us find the solutions to our problems. On your homework, you have quite a few poker hand problems, just to go ahead and throw that up there. Poker hands are nice in terms of most of us know what a deck of playing cards looks like, and if you don't, I would get familiar with them. You don't have to become a poker fanatic, but knowing that there's 13 of each suit, that there's 4 suits, that 2 of the suits are red and 2 of the suits are black, those kinds of things are helpful. So how many 5-card hands of poker can be made of all clubs or all reds? So clubs are like the clovers, they're black. So this is going to be a disjoint set because we have all clubs, that's a black suit, and we have all of our red cards. These do not overlap anywhere. You can't have a red club. So this is going to be a disjoint. And when it comes to our poker cards, the order doesn't matter. The order that they come up in my hand does not matter. And when order doesn't matter, when I'm selecting cards or choosing cards, I'm doing a combination. So it's not a permutation, it's a combination. So those are 2 things to consider. And then I'm going to just make a couple additional notes. If it's, most of your problems state that this is from a standard 52 card deck. I didn't type that out on all of these, but it's 52 card deck. which tells me half of my cards are red. And if half of my cards are red, that's going to be 26 cards. And since we're talking about clubs, that's a fourth are clubs. 52 divided by 4, there's 13 clubs. You go from 2 to aces. So why do I need to do this? Why do I need to know that there's 26 red cards and there's 13 clubs? Well, because I have to figure out how many different ways I can select these. How many different ways can I select an all red hand or an all club hand? So if I'm selecting an all red hand, then that means I'm selecting out of 26. I'm not selecting out of the 52 because I need to select all red. So I am choosing out of 26 red cards, and I'm choosing 5 at a time because I need to have my full hand be red. If I want a full hand of clubs, that's going to be picking from 13, but again, I'm choosing 5 at a time. So my starter numbers are smaller because I have limitations. It's not just any random card out of that 52 deck. I'm looking at these smaller subsets. Well, if I do 26, choose 5, I get 6, 5, 7, 8, 0. There's a lot of ways to get an all red hand. To get an all club hand, there's 1287. For a grand total of 67,067 ways to get either an all red hand or an all club hand. And we could interchange some of these words. We could get an all black hand and an all diamond hand. We could interchange those because those are two disjoint subsets of our actual 52 card deck that have the same number outcomes. I could compare red, I could get an all red hand with an all spade hand. That would give me the same solutions. So sometimes you have to do multiple combinations in order to get to your total because there's different limitations or your ORs are disjointed. Are there any questions on this problem? We have a lot of problems like this on the homework. And we have 2 more card problems coming up. Okay. Let's look at this table of... this one's congressional members. In your homework, it was senators. It's the same difference. They'll give you a table. It says the table below categorizes the diplomatic delegation of 18 congressional members as to political party and their gender. If one of the members is chosen randomly to be the spokesperson for the group, and how many ways could that person be a Democrat or a woman? So the first thing we have to do is determine, are our groups disjoint or not? Do we have any overlap between our Democrats and our women? AKA, do we have any women Democrats on our table? We do. So these are not disjoint. I'm just making notes. Disjoint. Because there are 6 women that are Democrats. So they're right there on our table. So since that's not the case, we're going to have to use the longer formula. And I'm actually going to choose to write it out so we can see where it is we're putting in all these details. So we need the number of people that are either Democrat or women. The or translates over into a union. Democrat or women. But we have to make sure that we take out any Democratic women so that we're not double counting them. So I'm going to have to find the number of Democrats, add to that the number of women, and then subtract from that the number of Democratic women. Or I guess the better mathematical way to write this is the Democrat intersect women. It's the Democratic women, but the intersection of those two. So how many total Democrats do we have in our table? 10. And how many total women do we have in our table? And then how many Democratic women do we have in our table? 10 plus 9 is 19 minus 6. There are 13 different ways we could select a spokesperson for this group where they would either be a Democrat or they would be a woman. So using unions and intersections of our sets actually helps us. With a table, you could cheat. I say cheat. It's not really cheating. It's using logic. And you could say, well, there's 9 ways to pick a woman. And if I can't have a Democratic woman, there's only 4 Democratic men. 4 and 9 gives me 13. That's also going to work. That's just using logic. That's one of the reasons why I included the table on the front page, is because you can do a lot of the same stuff using logic or arithmetic or these set theories. So I like using the sets right now just because it helps us to remember, hopefully, some of the Chapter 2 stuff and refresh on that before the end of the semester. But don't feel like you're anchored down and you have to do a certain way. All right, let's look at 3-digit counting numbers. It says how many 3-digit counting numbers are multiples of 2 or multiples of 5? It's actually a very similar process to what we just did with our Democrats and our women, because there are some numbers that are both multiples of 2 and multiples of 5, aka those that are multiples of 10. If you're a multiple of 10, you're a multiple of both 2 and 5. And so if we're trying to find out how many 3-digit numbers are multiples of 2 or 5, then we're going to be doing the same formula we just did. And I'm going to write it out in words. If you don't want to write it out in words, you don't have to. But I think it's a good reference so that we can draw the connections. We're going to take the number of multiples of 2, or, so that's a union, multiples of 5. We're going to figure out how many of them there are. So to do that, we have to find the number of multiples of 2. Add to that the number of multiples of 5. And subtract from that where they're both multiples of 2 and 5. It mostly fits on there. There we go. Okay, so I'm going to kind of be doing mini problems. I've got 3 little mini problems going on. I have to find how many 3-digit numbers are multiples of 2, how many 3-digit numbers are multiples of 5, and how many 3-digit numbers are multiples of both. And so when we do this, remember we can do using our fundamental counting principle. So our fundamental counting principle is where we looked at each of the digits of our 3-digit number and then we multiplied the different possibilities together to get our grand total. So I'm going to look at the multiples of 2 first. And we have a 3-digit number. So we have, I'll just list them in order so that it stays that way. First, second, and third. But it's our third digit that really is our limiter. Because to be a multiple of 2, what do we have to end in?
2, 4, 6, or 0.
Exactly. We have to end in an even number or 0. Those are our possibilities. So multiples of 2 will end in 0, 2, 4, 6, or 8. So we have 1, 2, 3, 4, 5 different options that can go in our third digit. What about our first digit? How many different numbers can go in our first digit if we're a 3-digit number? Okay. 10 is all of the numbers, yeah? From 0 to 9. If I put a 0 in that first spot, is it still a 3-digit number? No. So I got to take out 0. So there will only be 9 options for the first digit, the numbers 1 through 9. And then anything can go in that second digit. It's not going to matter. So to find out the total possible 3-digit numbers that are divisible by 2, I take 9 times 10 times 5. For a grand total of 450 different numbers. I'm going to do this process again for multiple of 5, and I'm going to do it again for multiples of 10. Again, for multiples of 5 for my first digit, I still only have 9 options because I can't have a 0 there. I'm still going to have 10 options for my second digit. My third digit, though, I need to be divisible by 5. If you're divisible by 5, you either end in 0 or 5. So I only have 2 options for my third digit. So I'm going to take 9 times 10 times 2 to where there's 180 different possibilities for 3-digit numbers that are divisible or multiples of 5. All right, last one is multiples of both. Or the other way to think of it is it's the union of these two. Or excuse me, intersection. So we still have a 3-digit number. First digit can be anything from 1 through 9. Second digit can be anything at once. Third digit, though, if we're divisible by both 5 and 2, I need to look at what ending numbers intersected. What did they share? And the only number they shared was 0. So that means there's only one possible ending for our third digit if we're divisible by both 5 and 2, and it's the number 0. So there's only 90 possibilities that are divisible by both. So to find the total number of 3-digit counting numbers that are multiples of 2 or multiples of 5, we will take 450 plus 180 minus 90, because those 90 represent the overlap, shared, to where we have 540 possibilities or ways. There's 540 different numbers that are 3 digits that are divisible by 2 or divisible by 5. We did some problems like this on a much smaller scale back in 10.1 where we actually just listed all of them. Even just doing the number of 3-digit numbers, just consisting of the numbers 1, 2, and 3 with repeating, we found that there was 27, I think. And so I'm glad we have better ways now of counting to where we don't have to list out all those possibilities. Yes, it takes work, but I promise you we spent a lot less work doing this than actually writing those 540 possibilities. Do we have any questions or clarifications that I can make on any of these that we've done so far? The cards, the Democratic women, or here with our 3-digit numbers? The trick is to know what the third digit is, and the other trick is to remember that we can't include 0 in our first digit, because then it's no longer a 3-digit. All right, flip over on the back. Got 2 more card problems and then just a regular set, like a very generic set problem. If a single card is drawn from a standard 52-card deck of cards, that's how most of your card problems will start. It says, in how many ways could it be a king or a heart? A king or a heart. So I'm going to list, we have, if we are a heart, how many hearts are there? Yep, there's 13. Because a quarter of the deck is hearts. So there's 13 different hearts. How many different kings are there in a standard deck of cards? 4 kings. Now, the question is, are these 2 sets disjoint or non-disjoint? Meaning, do they share anything or not? Yeah, they're going to share that king of hearts. There's 1 king that causes a problem. So I'm going to add the number of hearts to the number of kings, but I'm going to remember to subtract my 1 king of hearts. So there's 16 different ways I could select a card from a standard deck and either get a king or get a heart. Okay, same start. A single card is drawn from a 52 deck of cards, 52 card deck of cards. And how many ways could you draw a club or a face card? So clubs, similar logic to the hearts, there's 13 of them. Now the face cards, though, how many face cards are there? Let's just think, how many face cards are there in clubs? Yeah, so this is a good one for me to make that distinction. They don't include ace as a face card. They include they don't include ace as a face. There you go, it rhymes. Don't include ace as a face. The only ones with actual people would be the jack, queen, and king, so there's 3 per suit. So 3 times 4, because there's 4 suits, would give us 12 total face cards. Sorry, that went off the screen. So the way that we're going to find this, if you want words, is we're going to take the number of clubs, add to that the number of face cards, and subtract the club face cards. So we said there's 13 clubs, there's 12 face cards, but if there's 3 per suit, that means there's 3 club face cards, which means there's a total of 22 different ways I could draw a card and either get a club or a face card. So any of your homework problems that ask for a face card, it's just jack, queen, or king. Aces don't count. Aces are not a face. I like that. I'm so using them. I like stupid things like that. So be careful. There are problems. This problem could change and say, in how many ways could you select a black card or a face card? Well, if you are selecting a black card, there's 26 different ways you could do that. If you're selecting a black face card, or a face card, there's still 12 ways, but you're going to have black face cards. That includes 2 different suits. That includes your spades and your clubs. So if they get a little bit broader on their asking, which I know they do, they asked in one of the homework problems, or at least one that I got, they asked how many ways could you draw a black card or a queen? Well, there's 2 black queens, so instead of subtracting 1 or instead of subtracting 3, I would be subtracting 2. All right, we're going to do one more. This one actually kind of ties back to the not at the very beginning of this section. It says, in how many subsets of a 25-element set have more than 3 elements? So when you take a subset, you could take a subset, like we have 25 different items up here on the table. I could not take any. That's the empty set. I could just grab 1. That's a set of 1 item. I could grab 2. That's a set of 2 or 3 or 4. But obviously, if I grabbed this red thing over here, I could have grabbed this green thing over here. And if there's 25 items, then there's 25 different ways I could make a group of 1. So there's tons and tons of different possibilities that are going to happen here. And I have to figure out how many subsets can have more than 3 elements. Well, there's a lot of numbers between like 3 and 25. That's a lot of work. So we are going to consider the subsets with less than 3 elements. We're going to do the opposite. We're going to do not. Not more than 3. I should write more than, because that's the important part. More than 3. Not more than 3. So if you're not more than 3, let's consider if we have 0. This one might seem a little bit weird or seem like a moot point. But if I have 25 elements out there and I don't take anything, how many different times can I not take anything? How many different ways that are unique can I not do that? You have 1 subset. And you can even do it here with our combinations. If you do 25 combination 0, where we don't take anything, there's only one way not to take anything. So there's 1 subset. If I'm going to do subsets with only one element in them, that would be 25 choosing one at a time. Well, that's going to be 25. And this always works. If you're only choosing one item at a time, whatever your starting number is how many different subsets you're going to have. Hopefully that makes a little bit of logical sense. All right, let's do if we are taking things at 2 at a time. If we're having subsets with 2 elements each, we're going to have 25 combinations of 2 elements each. How many different subsets is that? $300. There are 300 different ways to choose 2 items off of a table of 25. That's kind of crazy. Now, we don't get to stop here because it says more than 3 elements. That's what we're actually we want to consider is whenever our subsets have more than 3. It doesn't say more than or equal to 3. It says more than 3. So to have more than 3, we'd have to have 4 elements. So I still need to consider one more subset whenever we have 3 elements in it. So that'd be 25, choose 3 at a time. You guys can tell me how many you get. It's quite a few. 2,300. Wow, that's a big jump. We added 2,000 more subsets just in that one leap. So if we add all these together, there's 2,626 subsets with 3 or fewer elements. Which is great, except that's not what they asked us for. That we found the not. But the not's actually easier because I don't want to do that process for 4, 5, 6, 7, 8, 9, 10, all the way up to 25. Do you see how we only had to do it 4 times instead of doing it 21 times? Doing the not saves us some work. But we're not done. Because when we use the not, we have to know how many total possibilities are there in our universe. Well, to find the number of subsets of a 25-element set, we have to take 2 to the n. And our n in this case is 25. So we need to figure out 2 to the 25th power, which is actually kind of a fun number. 3, 3, 5, 5, 4, 4, 3, 2. Hold me accountable on that, because just because it's a fun number doesn't mean I didn't leave something out. I very much could have. 3, 3, 5, 5, 4, 4, 32. So that's how many total possible subsets we can get. So then we're going to subtract from that our not, our 2626, to find out the total possible subsets where we have more than 3 elements. 3, 3, 5, 5, 1, 8, 0, 6. 33,551,806 possible subset. I guess I'll write subsets, not ways. There's a lot of different ways we can rearrange or select items when we start with 25. And it's much easier to consider the couple of instances here where our requirement was not met than thinking about all the different possibilities when our requirement is met. We like to work smarter, not harder.